Uh, Good morning, everybody. No, please. Go ahead. So what we're going to discuss today is so the last two bits of the course. The first lecture is going to be about band structures, and the second bit is going to be about trying to go beyond the local density approximation and also beyond the DFT. Okay, so that in this first part we will discuss basically what can be calculated in terms of electronic structure. In the second part, we will essentially review a few of the techniques that people use today that are becoming quite common, so that maybe you have an idea of the names and the keywords that people use, and you can associate with some of the discussion we had at this point. So surprisingly, when you discuss band structures, the techniques are much simpler than what we discuss for phonons and dielectric constants, because a band structure is essentially a bunch of eigenvalues, Kohn-Sham eigenvalues, and you've been calculating them throughout this week. Basically, every time you perform a calculation, it has to go through eigenvalues. So band structures is just a way to line them up, visualize them. Okay. So just to give a general idea for those who don't remember what happens in solid-state physics courses. So the key observation when you discuss band structures is that in extended solids, so where you have a crystal, the unit cell is repeated periodically, and because of that, it is always possible to write down the wave functions as the product of of something which is periodic, so which is repeated identically in each unit cell, and something which looks like a complex exponential where there is a wave vector and the position. Okay, so that's called a block theorem, and it's the first thing that one studies in solid-state physics. There is nothing really complicated. So this is an example where you have the again graphene, and I'm using that just because it's two dimensions, so it's very easy to visualize. The unit cell. The unit cell is defined by the vectors of the primitive lattice, so A1 and A2. Contains two atoms, and basically if you translate this direction here or any integer multiples, you generate the entire lattice. So from A1 and A2, we said maybe a couple of days ago that you can generate the primitive vectors of the reciprocal lattice, which are B1 and B2. So these are dual vectors to this one. So in the sense that if you do scalar products of this with that, you get like a Kronecker delta times 2 pi. And from this, you can obtain essentially the entire reciprocal lattice, but in particular, you can define the first Brillouin zone. Okay. Just as a reminder, the Brillouin zone is found simply by taking the smallest reciprocal lattice vectors, okay, cutting through the middle with a perpendicular line, and taking everything which is on the side of the center of that zone. So this one, here you cut, take this one, here you cut, take this one. So that defines basically a closed area in this case, and that's the Brillouin zone, the first Brillouin zone. So why people are interested in that is because if you try and calculate a block wave function at any point outside the first Brillouin zone, that is going to be identical to what you would find inside the Brillouin zone by translating your wave vector by a reciprocal lattice vector. So everything is identical also in reciprocal space. So one restricts the description at this point. And in terms of calculations, you've seen already the flag or the keywords k points in the calculations. So when you were selecting a grid of k points, the idea was to basically place a few discrete points in this area or in a volume in 3D in order to represent this, to sample this region. Okay, so in most electronic structure codes for solids, one solves the Kohn-Sham equations by essentially specifying the various wave vectors k and solving each equation for a specific k vector. Okay, so that means that the eigenvalues that you obtain as a solution, they will carry a label. Okay, and the band structures are just obtained by plotting this number as a function of the three-dimensional wave vector k. So in principle, we have one function in 3D space, but since there are several bands, there is also a band index, so you have several sheets that you need to plot. To give an idea of how this looks like in the case of, in the simple case of graphene, I'm just placing here a plot of of a simplified band structure. So that's not DFT. That is a very, very simple two orbital type binding model, okay, of graphene. But that gives you an idea of how the band structure would look like. The Brillouin zone is two-dimensional, so it's a region in a plane. And when you try to plot the band structure, well, there is an eigenvalue for each point of this area. So basically, it's a two-dimensional surface. So since we have two orbitals in this type binding model, there will be two bands, and therefore there are two sheets, okay, 1 and 2. So that's basically what you obtain. So you must have seen pictures like this all over the place. So the Dirac cones would happen here, essentially, at the K points in the Brillouin zone. This one, this one, this one, this one. So that's still fine, and you see many plots like that for like graphene, but or other 2D materials. Problem is that if you try to do the same plot in 3D, you get in trouble because the Brillouin zone is no longer a region in a plane, but it's a volume. Okay, so you would have to plot a function which is a volumetric function, so it has to be somewhere, and this also has multiple sheets. So even if you want to do a color plot, you would have to have several of them to represent the various bands. So it's a mess. So people clearly are smarter than that. So what they decided is to do to develop a simplified representation where instead of plotting the eigenvalues at each point of the Brillouin zone, they say, so if you look at this Brillouin zone of graphene, for instance, so this triangle, okay, is probably identical to what is going to happen here. So here the picture is a bit kind of, I don't know, stretched horizontal, I don't know why, but so everything is identical, right? So if you can sample this region, probably that will tell you everything about this region, this region, this region, this region. So by symmetry, you don't need to do everything. You restrict the bands to a region. And also, in this triangle, basically, probably you can use mirror symmetry here to just restrict your description to this bit. So this portion of the Brillouin zone, in the case of graphene, is called the irreducible wedge of the Brillouin zone. Okay, when you read the irreducible wedge, it means that. And each Brillouin zone in 3 dimensions has a irreducible wedge, which is basically the minimum amount of minimum volume that you can take, and from which you can generate the entire Fermi Brillouin zone using symmetry operations. So the idea here is not to, again, plot something inside the entire thing, because the assumption is that if you are here, for instance, and you move towards the inside of this region, maybe the energy eigenvalues will not change that much, okay? So one can use a simplified description where you follow a line like that, and you do a one-dimensional plot. So this is basically from gamma to k to m to gamma. So gamma, k, m, gamma. So that's basically a loop. So this, you have to imagine that this plot is vertical here. So basically it's eigenvalue going like this in this thing. And then it's plotted basically by unfolding this line. And so each segment is separate. So this is that, and but they are basically put together afterwards at the end. So that's what a band structure looks like. And it's something probably you know from when you were in kindergarten. But it's useful to remember sometimes. So this is more something a bit more realistic. I'll go that side. This is basically a DFT calculation of the usual two suspects, silicon and diamond. We've been doing calculations on that throughout the week. So you see, basically, they are very, very similar, these band structures. So the reason is that they essentially have exactly the same structure, which is the diamond structure, and they are just one on top of the other in the periodic table. So the chemistry is essentially the same. So here the situation is slightly more complex for the Brillouin zone. You have a 3-dimensional volume, okay? And that's always the case for these FCC crystals. The Brillouin zone is basically something which has 1, 2, 3 on the back and 4, then 4 at the bottom, hexagonal phases, and then 1, 2, 3, and 4, 5, 6 square phases, okay? So that's a typical thing in FCC crystals. So in this case, basically, the reducible wedge is something which maybe you can see here, okay? So the idea is to just go around this loop from gamma to the center of maybe one of the edges of this hexagonal face to a vertex here, and so on. So there are clearly several choices. That's also why sometimes you see band structures where you have a lot of, kind of a lot of segments, and sometimes you have only a couple of them. It's a completely arbitrary choice. It depends on what the person doing calculation wants to show you. Okay, so there is no, it's completely, essentially, in principle, you would like to sample everything, but sometimes the information contained along some lines is completely trivial, you don't care. So this is basically why sometimes you see very long band structures, sometimes very short ones. So in this case, what we can tell is basically along this path, for instance, that these are the valence bands, and you discover basically that by simply counting how many electrons. In this case, it would be 4 per atom, so 8 electrons per unit cell. Each state is occupied by 2 electrons because it's been compensated. So there will be 4 bands. So it's 1, 2, 3, and 4. So these are the occupied bands throughout. And everything above is empty. Okay, so these are the valence bands. These are the conduction bands. And then you can determine where is the top of the valence band, and you do that basically by inspection. So it's here, so a gamma, or here. And then the bottom of the conduction band, in this case, you find it here. Okay. So from these kind of things, people make statements like, oh, this is a indirect bandgap semiconductor because the top and the bottom are not at the same wave vector. And that's pretty much it. There is not much more that one needs to know. Maybe one observation that people discuss things like so what is the size of the bandgap in this case? So it's this region here where there are no eigenvalues. And what is the size of the bandwidth, which is basically the difference between the top and the bottom of the valence band. So for instance, when you go from diamond to silicon, the bandwidth goes from, I don't know, here it's 22 electron volts to 12. Okay. So this is related to the fact that the carbon-carbon bond is shorter. So if you use tie binding arguments, you can explain most of these trends in simple materials. Okay. So that's pretty much it for very, very simple structures. Other situations are more complex. These are pretty nice. So this is a slightly different case. So far we did only semiconductors, basically, so systems with a gap in the tutorials. So this is an example of a metal, okay, just to complete the picture. And that's probably the simplest possible thing you can calculate beyond the alkali metals. So that's the band structure of copper. And I'm putting here the periodic table just because I want to make a point about what we are seeing here. So in the case of copper, basically we have 4s2, and then there is 3d9. So what happens, and so you may imagine that actually copper will have some d states at the Fermi surface. That doesn't happen basically because it's more advantageous for the copper atom to have 1 electron from the s manifold to be in the d states. So that becomes a complete shell, and we are left with 4s1. So that's also why copper behaves like an alkali. It's basically a very good conductor. It's a perfect, electron gas. So it's a very, very simple system. So since the d states are all filled, okay, you can imagine that they will not basically be near the Fermi level where things are half occupied. So in fact, if you look at the character by plotting the wave function, you discover that these things corresponds to the d states. Okay. So this is something which is described already in the book of Ashcroft and Mermin, if you go there. The difference is that here you can verify that by yourself. You can perform a calculation, then you plot the wave function. We will do that today in the afternoon, and you see that these things are copper states. So what is left is the 4s states. And I think what is interesting in this story, that's really a nice pedagogical example, because if you forget this bit in the middle and you try to imagine connecting this line here with this, so it looks like actually that you have a electron gas, so a parabolic dispersion, intermixed with some kind of d states. Okay, so this is really the simplest possible situation you have. That's why one can describe copper as a free electron gas in practice, because very near the Fermi surface where things matter for electrical conduction, you almost have a parabolic kind of dispersions. So energy equal h bar square k square divided twice the mass. Okay, so that's the simplest system that you ever see in electronic structure. So now I just want to show you a Fermi surface, which clearly you've seen because it's something that you know in Kittel is like in the second chapter or something. So if you take a electron gas, so that's K, and that's the energy. When you define the Fermi energy, which is basically the highest occupied state, that essentially hits the dispersions at certain specific points, which are basically the Fermi momenta. Okay. So you may wonder what is the surface in K space which corresponds to wave vectors with energy at the Fermi surface, also at the Fermi level. So that surface is a sphere. Is that obvious? So if you got this parabola and you ask what are in 3D all the wave vectors with the same energy, there is only a possibility. It's a sphere. Okay. So the Fermi surface of a free electron gas is a sphere. That's it's something it's really undergrad things. So now in this case, you can imagine that basically this will also be almost a sphere because we have almost a parabola. Okay, if you follow this curve. Now let's look again 1 second at this. So this is the same Brillouin zone for diamond, silicon, and for copper. Okay, so the L point is on the center of the hexagonal face. Okay, so what is happening here is that the intersection with the L point, so basically the intersection of this kind of parabola with the Fermi level is past the L point. So what we expect is that if we try to draw the surface, the Fermi surface for copper, the connection point will be outside of the first Brillouin zone. If you look, for instance, at X, maybe, do we have X? Yes, here. You look at that. So the intersection between the parabola and the Fermi level is just before the X point. So if I go back here, so basically I expect a bit of surface to be inside the Brillouin zone. So one bit will be inside, one bit will be outside. If you now try to do a plot of the Fermi surface, essentially plotting all the wave vectors which have energy at the Fermi level, so you find this thing. So what you can see basically is that if you go near the X points, okay, here, the surface does not cross the Brillouin zone boundary. And if you go to the L points, basically there is no, so the crossing point is outside of the first Brillouin zone. So that means that you will find some necks in the Fermi surface. So simply because this point is not inside here, but it's outside. Okay. So this is a way to understand these Fermi surfaces. So that's something now that it's actually quite impressively accurate. If you do measurements of these Fermi surfaces using quantum oscillations, so that's the Haas Van Alphen. I mean, you can actually measure the frequency of revolution around these necks or around the various diameters of the Fermi surface. They come out quite good actually. So it's really quite impressive how you can calculate Fermi surfaces which are in very, very good agreement with experiment. And typically even calculations on well, I mean, this is a bit more controversial, but things like pnictides and more complex metals, the agreement between DFT and quantum oscillations is very good actually. So that's interesting. So this is an example of wave functions. Essentially, 1, 2, and 3 just mean what I did is to pick electrons at the Fermi energy at this wave vector, and this one, just to show how they change across the Fermi surface. So there is a little bit of change, okay? So maybe some of these orbitals will be D-like, okay? But clearly there is a small component of D, and there is a main component which you see it's really covering the entire unit cell, and that's basically the S character of the wave functions. So that's how electronic states would look like in a two-dimensional slice on the Fermi surface. Okay, this doesn't tell you anything spectacular. It's just a way to understand a bit the system, and it is useful when you are making some discussion in a paper, and then the referee asks you, what is the character of the state, and then you show a picture, and you discuss what that is. But what really matters is what you can calculate and how you can compare to experiments. So this is difficult to compare to experiment. So at some point you can also do something fancier. We will not do that. So this actually takes a bit of time. Rendering something like that it may take a couple of days. So actually this is what happens when you're a PhD student in a theory group, when your supervisor tells you, well, I want a spectacular figure because we want the cover, and then you spend your week doing that. So that was one of my students now at NUS in Singapore. And that's basically a much more complex system where you have basically a zinc oxide substrate, a polytriaxylthiophene polymer on top. That's the HOMO level. So these things are useful for electron injection or extraction from in kind of heterojunctions. Okay, so this is the kind of thing you can also do, but you do them once in a while when you really want to do something fancy. So most of the time it's something much lower level. So now we discuss band structures, and I would like to ask a question which sometimes, sorry? The question is basically, are band structures real? Because we're discussing Kohn-Sham eigenvalues, okay? So that's a solution of Kohn-Sham equations, which are needed to obtain the electron density, which is needed to calculate the total energy. And all these things were artificial in a sense. So it's all a mathematical construct to get to the total energy. So that's the only thing that matters in DFT in practice. So one could say, we're discussing the eigenvalues of the Schrödinger equation, but do they have any meaning in practice? So I think we're going to try to answer the question by performing a comparison first. So this is a comparison between the angle resolved photoemission spectrum of boron-doped diamond and the DFT calculation of band structure of diamond. Okay, so the reason why in ARPES they need to do boron doping is that you cannot do measurements on an insulator, otherwise you have problems with charging. Okay, so the boron doping makes it into a metal basically, but the band structure doesn't change with respect to the standard insulating diamond. I mean, it doesn't change on this energy scale. It will change a little bit here. So what I should tell you is that, so what is how a ARPES experiment is performed. So we could spend a week discussing that, but in the simplest terms, what you need to imagine is that I guess some of you have seen the setup upstairs or other building. Yeah. So basically, you shine photons, okay, on a sample, and essentially by the photoelectric effect you can extract some electrons. Okay, so you know the photon energy, so you know how much energy you are giving to the sample. You can assume that the entire energy goes to one electron. Let's forget how good or bad is this approximation, but let's assume that. So you know the energy, then some electron will be ejected, and there is an analyzer which is this half sphere, the MI spherical thing, the shiny thing that you see near the MB, that basically records two things: the kinetic energy of the electrons which have been extracted, and the direction of flight, basically. So basically, if you have the kinetic energy of the electron, the outgoing electron, and the photon energy, and you know also the work function of the material, what you can determine is basically how deep the electron was inside, like in terms energetically, in this material. So how far from vacuum the energy level was, I mean, before exiting the sample. The second information is that if you have the angle, so the exit angle, that gives you, since you are talking now about a free electron flying in vacuum, okay, that gives you an information about the momentum of the electron, okay? And by using some very simple conservation laws, you can tell that that momentum is, probably very representative of the momentum of the electron before exiting the sample. So there are some issues like conservation momentum along the direction, so perpendicular to the surface or parallel, but that's technicality, so we won't not discuss that. But I would say that this is probably in this kind of experiment, what is nice is that this is really a direct measurement of where electrons are in terms of energy and in terms of momentum. Okay, so that's probably the most direct way of measuring that. So we can imagine this to be kind of a picture of experimental picture of a band structure, and when you compare that to the Kohn-Sham band structure, well, you can see here that things are quite similar. Okay, so in this sense, what you could say is that, well, maybe, so these things are real in the sense that you see something similar in an experiment. So there must be at least some kind of degree of realism in this calculation. Okay. So let's maybe be slightly more accurate in what we are saying. So here we're really talking about a situation where you basically trying to measure what you're really measuring when you do this. You know the energy of the photon, you know the energy of the outgoing electron. You're not measuring the energy of the electron inside the sample. What you're really measuring actually is the difference in energy between the sample before the experiment and the sample after having removed an electron. Okay, it's really a difference in two total energies, one with a certain number of electrons and one with that number minus one. So it's a difference on two total energies. So the question is, how is it possible that just eigenvalues can correspond to differences in total energy? So to understand that, actually, what is useful to do is the following. So if you take the expression for the DFT total energy that I showed you maybe on the second day, okay, maybe there was, lecture 2.1 here. So you remember we had the total energy equal something like there was basically the integral of the density with the external potential of the nuclei. There was the Hartree energy. There was the exchange and correlation energy, and there was the kinetic energy. Okay, so there was an expression for the DFT energy. So you can actually, if you go to the chapter, I guess 9 of the book, you will see that that expression can be rewritten equivalently in this form. So what we discussed in lecture 2 is identical to this. Okay, that's just a different way to write it, which is slightly more clear for this discussion. So why I want to write it like that? Because the reason is that basically you can try to write down the energy as a sum of eigenvalues of the occupied states. So that's basically is 1 for occupied states and 0 for unoccupied states. Okay? And then there is another term, which is called the double counting term. I mean, it's whatever is left. Okay? So that's exact. I mean, in terms of it's an exact rewriting of what we did in lecture 2. Now, what we can do is the following thing. Let's assume that this bit is very small, or doesn't matter very much, okay? Just an assumption. Then what is going to happen is that if you start from a situation with all, let's say this is a band structure, all these states are occupied, okay? You are basically counting the eigenvalues for each of these states. Assume that you are removing an electron from this state, okay? What is the difference in energy between the original configuration and the one without an electron? That difference is precisely the eigenvalue of this electron, right? Because we are saying that that is the energy. So basically, the eigenvalue represents how much energy you are adding or removing when you remove that specific electron. Okay, that's the simplest, most naive way of looking at the problem, and that's actually the reason why these eigenvalues have some meaning. Now, in a sense, what you could say, so there are two schools of thought. Some people telling you Kohn-Sham eigenvalues don't mean anything because they were derived and blah blah, starting from a theory which gives only the density and the energy. But if you look at eigenvalues in these terms, clearly they have some approximate meaning. Okay, so the problem is that the total energy that is actually different total energy, which is measured by RPES, is not just that, but there is another bit here. So that should explain why these eigenvalues are not, completely faithful description of these total energies, because we are neglecting a complete bit here. So if you want to be technical, we can also say something more about that. If you imagine removing just one electron out of a lot of electrons, so basically an infinite crystal. Let's think of silicon, where basically the top of the valence, suppose, is completely delocalized. There's a nice electron, a nice block wave everywhere. So the change of density, if you do that, is infinitesimal, right? Because the electron wave function is normalized to 1. So if you have a gazillion electrons, you remove one, the change of density is basically going to be negligible. So the change of Hartree energy will be negligible. The changes of the density here will be negligible, okay? And one could say, okay, but then it's done, because maybe this is negligible as well, and that's fine. Okay, so actually we can use the eigenvalues that are a very good representation of. So there are two catches. First, now it is well understood that actually this object, the exchange correlation potential and then the energy by consequence, actually have essentially they jump if you change the number of electrons. So there is a discontinuity. So even if you do the limit of density going to 0, delta density, the change of this and that will be finite. So there is a problem there, and there is a discontinuity. And that is also at the origin of the fact that DFT cannot give you good band gaps in the local density approximation. Okay? So that's a fundamental problem. The other problem you can imagine is that now I made basically an example of silicon with a completely extended wave function. Okay? So if you remove an electron, the change of density is going to be completely negligible. Now let's consider another example where you have, I don't know, a Mott insulator. If you remove an electron, which is coming from a 3D state, which is extremely localized, well, that change is going to be felt by the system locally, okay? So that assumption that this and this is negligible doesn't hold anymore, okay? So that's where these things come from. So the things like Mott physics and all these things are not, far away from this, actually. Everything is embedded in all these expressions. It's just a different way of looking at the problem, okay? But in principle, band structure will look okay mostly because of this thing, basically under the assumption that is not too big and doesn't change too much, okay? But if you always keep in mind this difference, you can use band structure to make discussions, and maybe you can answer people who tell you that they don't mean anything, okay? There is no exact meaning, but from a point of view of total energy, they can be seen as some kind of reasonable, first guess on, changes in total energies. So in the second lecture today, we will discuss, a better approach to, look at total energy differences. So since there is this problem with the discontinuity in these potentials, or sorry, exchange correlation potentials, the practical outcome is that when you're trying to calculate band gaps, they come out quite wrong, okay? So this is a plot where what I'm showing is basically the band gaps calculated for some semiconductors and insulators, okay, compared to experiment. So the way to see the plot is the following. Let's take, I don't know, magnesium oxide. Experimental band gap is here, okay? If the calculated band gap was like in experiment, we would fall on this line, okay? Okay, it's fine. So sorry, it's just magnesium oxide. It's not, doesn't hurt. It's okay. And so basically, we'll be on this line if it was perfect, but it is not. So actually, we are below, and maybe this is, I don't know, 5 volts instead of 8. Okay. So if you look at the others, essentially, what happens is that instead of falling on this straight line, they all a bit below. And that happens, on the regional large band gaps. If you zoom here, these are small band gaps. It's the same. So now one could say, well, there's some kind of trend. So what I could do brutally is to say, well, I can fit a line here, and whenever I get a DFT gap, I rescale so that I go back to experiment. So that's an approach which could work. So if you try to do the fit, you get essentially that in average is about 40% below experiment. Okay, the calculation. So the point is that one could do that, but so let's make an example. So for the perovskite I was discussing yesterday for the phonons, so the DFT gap is alpha volt, so 0.5, okay? If you do that times 1.4, so if you increase by 40%, that will give you, so using kind of an empirical rule, that will give you 0.7 volts. The experiment is 1.7, so you're off by 1 volt, okay? So it's quite dramatic. So the point is that essentially here there is in average maybe 40%, but the deviation, the scatter is very large. So it's really not predictive, and essentially the amount of underestimation is quite challenging to predict, and it will also depend on the character of the electronic states. It will depend on the physics of the system, and different systems will react differently. So something even more complicated comes if you look at the small band gap region. Let's say an example which is familiar to everybody. If you look at germanium, okay, it should be an experiment what 0.7 eV. Okay, if you look at a calculation, it's a metal. Okay, so actually it's not really a metal, it's a semi-metal. Okay, but it's still you will have essentially a Fermi surface in a calculation of germanium. Same story in scandium nitride. So you have problems like that where you expect to do a calculation of an insulator, so a semiconductor, and you end up with a metal. So at that point, it is difficult to convince your colleagues that you're doing something meaningful because it just qualitatively is not there. So that's basically one of the problems. And I think this is one of really the main things that exist now as a problem, in the sense that apart from the band gap, which is not really, one may say, what do I care about the band gap? The band gap affects the screening, so the electric properties. Screening affects many other properties, and sometimes even vibrations and things like that. So if you're really changing qualitatively what your material is like, then it's difficult to be able to trust everything else. So that's actually quite a central quantity, and I would say that this is not solved. I mean, it was still far from getting there.
Question: can you roughly explain why we have this underestimation?
Yeah. So basically, it's well, there is basically in this term, this and that. So this will drop. This will be identical to the ground state in the limit of large systems. But this thing has a discontinuity when you add or remove one electron. So, this object depends on the density, okay? Yeah. But nobody has ever said that it has to be a smooth function of the density. So there are some, kind of studies which show that this function, if you change by 1 the number of electrons, there is a discontinuous jump.
So the exchange correlation term is not continuous with respect to the density?
Yeah, correct.
But, and can you just say what is EH here?
That's the Hartree energy.
Oh,
yeah, that's basically density divided by the distance between two electrons. That's completely continuous.
And I still don't really follow why the discontinuity will make that problem.
Oh, because if you look at the, so if you have a band structure,
yeah.
Okay, what you end up with in terms of band gap is the difference between two eigenvalues. Okay, and what it should really be is the difference not only between the two eigenvalues, but also that should include a jump in this function. Okay, in the local density approximation, this jump does not exist. So the exchange part, if you remember, is the density to the power of 1/3. So if you change the number of electrons, that changes smoothly.
So it is because we use LDA.
It is because we do not know the exact exchange and correlation energy, basically. Yeah. So in exact DFT, so if you were able to write down a exact exchange and correlation function, and you calculate total energy difference between the system with n electrons and n plus 1 n minus 1 electrons, that would be the ionization potential. Okay. So now I want to discuss something slightly different because there is an exercise today on that. So what can we do with band structures? So the exercise, I don't know if you managed to do it because it's quite long, but it's there, it's all explained. So if you are interested in calculating optical spectra, you can try. So one of the applications of band structures is looking at, optical properties, for instance. That's the simplest way of studying the optical properties of a solid. And it is, so this expression, you can find it in the book of Peter Yu and Manuel Cardona. It's something which comes from time-dependent perturbation theory. Has nothing to do with DFT. It's just assuming that you know a band structure and you know the wave functions of your system. And that basically gives you the imaginary part of the electric function, which, it's the optical absorption. So proportional to optical absorption. So the other day, basically, so yesterday we seen a situation where we have absorption here, frequency. At some point it was going like that, and there was an excitor, and then going like that. So we're discussing the IR in this region with phonons, okay? So this bit here is this part, okay? So it's above interband transitions. So this expression, if you want, is explained and derived in the book if you're interested in the details. So I will not go through the details, but I just want to give a few comments on that. Just to keep in mind what happens when you see a calculation of this kind of properties, okay? So first of all, let's consider, as usual, silicon, where basically variance bands, conduction bands. So what this expression is telling us is that if you are looking at optical absorption, first of all, in this expression, you only find differences between conduction and valence states. So C stands for conduction and V for valence. So you can only do transitions from valence to conduction and never from conduction to conduction or things like that. So it has to be from occupied to unoccupied. That's something it's quite trivial, but it's, sometimes people get confused. The other thing is that people say, oh, you need to do energy conservation when you study these things. That's only a statement about this Dirac delta function, okay? So what this means is that you can only have transitions if the difference between the occupied and unoccupied state matches the photon energy. So if the photon energy is something like this, so there is no way for me to go from valence anywhere into conduction, so there is no absorption. If the photon energy actually is larger than the gap, at that point maybe I can find some matching here, and therefore I can have absorption, okay? That's what people call energy conservation, okay? That the energy of the final electron has to be equal to the energy of the initial electron plus the photon energy. But really this is only a statement about a mathematical equality. I mean, it can be interpreted as energy conservation, but it's a result of the basically time-dependent perturbation theory. The other thing that you notice here is that whenever you have this kind of transitions, the wave vector here and here are the same. So it never happens that you make a transition from, let's say, this point to this point. It has to be like that, like that, like that. So basically, you move vertically in this plot. So these are called direct transitions. And the last thing is that the strength of a transition, okay, is proportional to what is called the electric dipole matrix element, okay? So from the point of view of perturbation theory, what one does is to look at a perturbation Hamiltonian, which is the electromagnetic field, basically. So it's going to be proportional to exponential IQ dot R. And the electric dipole approximation is to consider the long wavelength limit, so Q going to 0. So what is left is just the position of the electron. So this and that are essentially identical if you consider this denominator here, okay? These two things are just a different way of rewriting the same thing. So that's basically what typically people discuss, and when people talk about dipole matrix element, it's this thing which enters these kind of expressions. Now I want to give you an example how this works. This is basically a calculation of the electric function of silicon. The expression I gave you before is the imaginary part, okay? And you can get the real part again by Kramers-Kronig, as in the case of the infrared absorption. So what we see basically is that the experiment, something like that, so black line, it's a function of photon energy, and you can see that we are in energies which are typically above the band gap. So it's not like vibrational energies, but we are like in visible or above the visible. Well, this is actually, this is basically visible. And you can see the theory is similar, but it's a bit kind of shifted towards the left. So if you look at the imaginary part, clearly these two things are related because one is Kramers-Kronig transform of the other. In the imaginary part, this is the experiment. And the theory, again, is slightly shifted here, but also the intensity is a bit too high, okay? So one could say, okay, this is a disaster, what do I do? So this is actually, whenever you see calculations where people don't give too many details, typically they're doing something like that. So probably it's not very reliable, okay? So one quick fix is very simple. I want to show how well it works. And that's basically based on the observation that band gaps are underestimated. So if you look at this, the first transition has to be essentially at the band gap of the system, right? Because if you have a photon energy smaller than band gap, there is no allowed transitions, and it's never going to happen if there is a peak. So if the band gap is underestimated, clearly you expect to see peaks, below the experimental absorption. And that's precisely what you see here. Okay, so the onset is not here as an experiment, but it's a bit towards the left. So in this case, in silicon, the gap is about 1.2 volts. In experiment, is about 0.6 in calculations. And so in these DFT calculations, okay?
But that's the indirect gap. What's relevant here is...
Yeah, it's basically, okay, I can restate that. If you look at the direct gap here in silicon, what is maybe 3.2, I don't know, in experiment, and it's about 0.6 CV lower in theory. So actually, it's almost a redshift. In fact, you see that basically this is about maybe 0.6 eV lower. So what one could do at this point is say, okay, I don't know how to do better. I don't know how to I don't have the time to perform calculations with better techniques. So what I can do is to go back here and say, okay, I assume that my wave functions are okay, and I modify the conduction bands by just lifting everything up by 0.6 electron volts. So just to see what happens. So you know the experimental gap, you know your gap, you try to match them, and basically you shift everything up. So this thing has a name, and it's called the scissor shift. Scissor means you cut the bands in the gap and then lift up whatever you have. It's just a little trick. Now, the interesting bit is that when you do that, the real part gets quite close to experiment, basically, and the imaginary part in the same way. Now, the onset is almost perfect. This peak is captured. You have a little bump here, which is there. So with this little trick, actually, you can go a long way to match the experimental spectrum. So what is missing in this story? What you will see here is that so the shape of this is reasonable. Okay, so from the point of view of bands, having done this scissor fixes most problems in terms of overall shape. So there is a shoulder, there is a main peak. Here, this peak is a shoulder, and the onset is correct. So what one can do beyond this point? Well, in practice, at this point, you cannot do much. You need to move up to a higher level of theory. In practice, this expression that I gave you is what is called the independent particle approximation. So you're assuming that electrons, they're just completely independent in the system. When you have an excitation by light, you can just change the occupation numbers, so an electron goes up or down. What this is not taking into account is that if you promote an electron to the conduction, okay, it will change its wave function, right? So you remove it from an eigenstate, you place in another eigenstate, but you have no guarantee that the wave function is the same. So what is changing also is the electron density. But in this expression, that is not taken into account, okay? So in practice, one of the physical effects which is missing here is essentially the formation of excitons. Okay, so when you promote an electron out of its ground state, so you have to imagine you take an electron out of its position. At this point, there is an extra negative charge somewhere, but there is a lack of negative charge somewhere else. So there is a hole left behind. In the approximation we're using, those two things don't talk to each other. But you can imagine that if there is a net negative particle and a net positive kind of charge here, they will attract each other. So that's a Coulomb interaction that will decrease the energy of the system. And what that is going to do basically is to bring back these kind of things. Okay, so this is something which can be calculated using the Bethe-Salpeter equation, which is a technique used to study excitons. I will mention that at the end of the next lecture. But that, at this point, is getting very, very advanced. So there are not many groups doing calculations, beyond this point. So that's what I just said. And the other thing I would like to mention is that, so in this picture, in the case of silicon, as Darrell mentioned, this is an absorption which is at the direct onset. Okay. So if we go back to this, the onset seems to be around 3 volts, but the gap is actually really, I don't know, in experiment is 1.2, here is 0.6. So it should be possible to absorb something here. Okay, so that is in Kittel's book is what is called the indirect absorption, and it requires phonons. So here you cannot see it because actually in indirect absorption, so this is an experiment, right? It's really from this range to this range, so it's really, really small in the experimental plot. But one can maybe look at that by using a logarithmic scale. So basically, this is the experimental absorption of silicon. I think I took that probably from either from NIST or NREL, maybe NREL. It was happily stolen from. I don't know. Anyway, so basically so this plot is basically the absorption of silicon. This is inverse, wave numbers basically. So the absorption coefficient is basically, so the inverse of this number gives you how thick a sample has to be to absorb a certain fraction of light, okay? So that's what is used when you study absorbers. And what you see basically is that when you look at a logarithmic scale, so clearly there is something down to 3 electron volts, which is the direct absorption, which is very high. And then you go really way down, and you go, but there is absorption, down to the indirect gap, which is about 1 volt, okay? And if you do a calculation, the way I just showed you, you get this red line. So this is basically the indirect absorption is completely missing in these calculations. So how can you deal with indirect absorption, and is that important? Well, if you think about silicon solar cells, I mean, all the absorption taking place in silicon is in this range, okay? Because basically the solar spectrum stops more or less here, so there is nothing here. So all of it is indirect absorption. So how to calculate that? That's quite a challenging problem, actually. And so essentially what it requires is all the things that we discussed so far for calculating Mach structures, phonons, dielectric constants, everything together basically, with an extra ingredient which is called electron-phonon interaction. So if you put all of this together, you can actually calculate the indirect absorption and get almost spectacular, perfect agreement with the experiment. But this is just to mention. So we managed to do this like last year. So that's very, very new. I mean, it's until recently, it's been basically impossible to do this kind of calculations. So we're getting there, but it's on the advanced side, where basically electronic structure community is trying to push to gain ground where we didn't manage to go before.
Did you use scissors here?
Yeah, this uses assist. So yes, correct. Yeah, otherwise this would be displaced. So in practice, one could do something better, like I'll describe later, which is the GW approximation. It is just more time-consuming, much more time-consuming. So this was basically the first demonstration. So first we showed it is possible, and now in fact what we are doing is to go beyond that and try to do something completely clean, essentially. Yeah. Okay. So I guess that's the end of this lecture, and in the next one we will discuss what is left. So what are the typical keywords of calculations going beyond the FT that you will hear about. So it will be less technical and more descriptive, let's say. All right.